Okay. In the last lecture, we have investigated all the components of the particle swarm optimization algorithm. We examined the sequence of operations and all the statements which were included within the PSO algorithm. At the end of the lecture, we tested this algorithm with Rastrigin function. We selected this function specifically because it has a large search area and because it has a large number of local minimums. And we found that the algorithm was able to get the global minimum directly, and it didn't stuck with any of the local minimum values. This is perfect and good. Now I shall again try to test the PSO algorithm with another testing function, which is the sixhump. This is just to be sure that it works perfectly without any problems or errors. I will not change anything with the algorithm except introducing the sixhump related values. At first, I have defined, as you see here, the sixhump function. This is the same expression which we used before. This function is two-dimensional as the Rastrigin function also. And I have here in the PSO substituted the Rastrigin function with the sixhump function. And when we also found the fitnesses, we also introduced there the sixhump function. Here, fitness, sixhump of P, and as you see, where it is also, I think it is here, this one, and that's it. In addition to that, I have changed the bounds of the function to be exactly the same, which is specifically decided for the sixhump function. The number of particles is kept the same, and the number of iterations is the same. And everything here is okay. And when we implemented the PSO, we included here the sixhump function. Now, if I run this program, I will not explain to you the details, we shall have this answer. Remember that this function has this unique minimum value, which is -1.0316. We have met this value in other examples when we optimized this function by using Pyswarms and by using other methods. And the coordinates, X and Y also, as you see, one of them is negative, one of them is positive, 0.71 and 0.089. Previously, we got 0.085. So practically we are having the same answer. So this PSO algorithm works very nice, correct, and dependable, no problems. Okay, now again, I want to compare the performance of the PSO algorithm with Pyswarm's library. So, as usual, I define the function here. We are working with Rastrigin again. And the bounds, the lower and the upper bounds of Rastrigin are given here. These are within the bounds which are usually for this function. We have defined the options, which is the coefficients of the Pyswarms, and we have called the optimizer and passed there the function, and we have run the Pyswarms algorithm. If we run it now, you shall see that the value of the minimum of Rastrigin is practically 0, and X and Y are also 0. And this is the same answers which we have got when we used the particle swarm optimization algorithm in the previous lecture. Interesting to tell you also that in addition to Pyswarms, really, there is another also library called Pyswarm without S. Practically the same approach is used, but you can see here that even the Pyswarms is simpler than the Pyswarm. You directly here define the function you want to optimize and the data relative to the function, which is the lower and upper bounds, and directly you call the PSO, pass to this function the objective function with the bounds needed only, and you will get the answer directly. Concerning time, this takes not more than 2 to 4 seconds. If you run this program again, as you see, we have here the X and Y are equal to 0 in practice, and the Pyswarm also found the minimum directly, and it did not stack with any local variable, with any local minimum. So I think this is sufficient to feel confident either by working with Pyswarm or Pyswarms or by the PSO algorithm itself, you will get always the same answer. What we shall do now? As usual, I always solve the problem by using also another software, which is LabVIEW. So here we shall go to the file where we have LabVIEW. Here. And now we shall try to work with LabVIEW in order to get the same answer. So we want to plot the Rastrigin function by using LabVIEW. We open the program here. Okay. It is loading. Now, this is the front panel here. This is the block diagram. Here we use the plot surface in 3D function. Create plot surface VI. Now you know how we can get it because I explained this to you formerly. And also, in order to have the contour graph, we are using this plot helper. We can fix its name also, plot helper VI. We use for this purpose this very generic function which evaluates y as a function of x1 and x2. We input the start and end limit values as usual. Here they are. For the function Rastrigin, we take them low values, -4, -4. I can take it -5. No problem with it. And the maximum value is 5.12, 5.12. This is the limits as usual. This is the expression of the Rastrigin function. And these two strings x and y represent x1 and x2 because it is used here as a two-dimensional function. Now, if we run the program, we shall get, as you see here, the plot, and we shall see here the contour in the x-y plane. And this is the plot in three-dimensional space, and you can see exactly that it is as we have got when we drew it with the Python. So it is okay, no problem, clear for you, and we shall go and show you how we can find the optimum minimum of Rastrigin function. I am opening this VI, continue to LabVIEW, and now we shall show you the block diagram and the function which we used for this purpose. Of course, this function find all minima n-dimensional VI. This is really a very powerful and interesting algorithm. As you see, it seeks in the search space for all the minimas and gives you every time the captured minimum values, including the minimum value, the global minimum. The limits are given -5.12, -5.12, and the maximum plus 5.12 as given by the recommendations of the limits for this function. The expression of the function here is given here as a string, as you see, and these are the variables. So at the output here, we shall get the array which includes the coordinates of the minimums of the minima values and the values of the function, the local minimums which are there, including the global minimum value. If you go to the front panel and see what I have fixed for you here, as you see, there is a lot of minimum values included. This is the coordinates of one minimum value, which is the first here, 15.94. It has these coordinates, and this is the value of the minimum. This is another value of the minimum with these coordinates, and you go up to the last one here. The last one here is related to the coordinates here of the x and y. Look how they are very close to each other, as we have seen in the figure, the minimum values. And really here, if you look at the values here, you find that the most minimum value, which is defined by this algorithm, is 1. It is not 0, but 1. When it is 1, it is with these xy coordinates, 1 and 0. The closest one to this minimum value is 1.99. It is, look here, it is also very close, -1 and 1. So, because this is an iterative process, and depending on the accuracy of the algorithm, but as you see, this is a very nice thing here. You at the same time, you get a high number about how many pieces, how many locals we have cached. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 minimum values. And one of them here is the closest one to the actual minimum value, which is 0. If we run again here the program, we will not get the same values. It depends. So we can catch some of these. Oh, here we have caught how many? Maybe more than before. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 local minimums. And the smallest one of them, as you see here, is 1. As we have done before, it was about -1 and 1. Let us see how its coordinates. This is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It is, as you see, 1 and 0. The coordinates x and y with this minimum value, which is defined by the algorithm. Of course, if I run it again, I may get another. Yes. Very nice. It really works very well. And every time you find about 15 or 12 or 14 values of minimum for this Rastrigin function. But as you see, really, this algorithm here is to find all minima and not to find the global minimum. So in order to find the global minimum, really, we go to another example I have prepared for you. Yes, it is this one, which uses global optimization VI. This VI, as formerly I told you, it exists as the optimization palette, and here it is a global optimization VI. This VI, as I told you, dynamically calls the function which is going to be optimized. So I have to go to this sub-VI or template and show you the block diagram. And here in the block diagram, I have drawn several objective functions which were tested by this VI. But this VI now, this block diagram, the down one with x and y, two variables, really it represents how is the structure or the VI of the Rastrigin function. I have written here Rastrigin. And the output of it is considered as the objective function. Okay, now you have seen that we have connected to the sub-VI here, or to the template, this function, which is Rastrigin function. And now I have changed the limits to be the same for the Rastrigin function, -5, -5, 5, and 5. And now I run the program, and we shall see if it only catches and defines only the global minimum. Look, here are the iterations, here are the values. The value is 0. And the values of x and y is 0. And the position of the particles here, as you see, for x equal to 0, here -1, here 1, x here is equal to 0, and y begins from 0 to up, and here it is 0. So for x equal to 0 and y equal to 0, which is the coordinates here, we have got the best minimum equal to 0. So the function works very nice. It really selected exactly the minimum value after about 45 iterations, and the function works perfectly and everything is okay. So I think with this, we have come to the end of investigating the global, the algorithm of the optimization or particle optimization function. We have compared the performance of this function twice by using Rastrigin function and by using sixhump, and we have found that we have got exactly the same values as minimum. We have also compared the performance of this particle swarm optimization algorithm with the Pyswarms and with the Pyswarm libraries performance, and we have got also very similar values. And also at the end here, we have also compared the performance of this algorithm with the performance of LabVIEW designed VIs, and we have found here very interesting things, that we can get a high number of local minima values, and we can also find the global minimum values. Okay, so with this, we finish with this issue, and we shall move in the coming lectures, to another interesting works related to this subject. Thank you. Goodbye.